Hello dear students, today we will discuss particle in one-dimensional potential well of infinite height. So let us consider a free particle of mass m that travels only along x-axis and is confined between x is equals to 0 and x is equals to a by two infinitely hard walls, so that the particle has no chance of penetrating them. This is possible if potential energy is infinite at x is equals to 0, x is equals to a, and the potential energy is 0 between 0 to a. This is known as particle in one-dimensional potential well of infinite height and width a. So in the figure you can see a particle is struck here where the potential energy is 0. On both the sides the particle is confined between very high potential, that is V is equals to infinite. It is like a person who is struck between two infinite height walls where he cannot jump it easily and he cannot penetrate through the walls. So this is the condition of a particle in an infinite potential well. So here x is less than or equal to 0, and at x greater than or equal to a, v is infinity. So here v is infinity and here v is infinity, but here the potential v is equals to 0. Therefore psi is equals to 0 at psi is equals to 0 at x is less than or equal to 0 and x is greater than or equal to 0, because the particle is not present here. So the particle is present here, and here only we can get psi has some values. So we know the Schrodinger wave equation. This is our Schrodinger wave equation which we have derived. So here we have to substitute v is equals to 0, because here the potential energy v is equals to 0. That is the reason substitute v is equals to 0, and this equation is going to be changed like this. Now here this all term we will take it as the constant. That is the reason this all term we will write it as k square, where k square is equals to 8 pi square m divided by h square into e. Now the solution of this equation, the solution of the second order differential equation can be written in the form psi is equals to a cos kx plus b sin kx, where a and b are the constants. So you can see the value a and b, this a and this b are the constant values depending upon the boundary conditions. So depending upon the boundary conditions we have to find out these a and b values. So let us consider the first case. At x is equals to 0, psi is equals to 0. This is the first boundary condition. X is equals to 0 and psi is equals to 0. This is the first boundary condition what we are substituting here. So when you substitute x is equals to 0 and psi is equals to 0 in this equation, it is going to be 0 is equals to a cos 0 plus b sin 0. Therefore a is equals to 0, because cos of 0 is not equal to 0. Here you cannot substitute cos 0 is equals to 0. Okay, and that is the reason a is going to be 0. Now to find out the value of b, we will consider the second condition, that is here x at x is equals to a, psi is equals to 0. That is the second condition we are going to consider. So here we will take x greater than or equal to a, psi is equals to 0. So in this equation 0 is equals to a cos ka plus b sin ka at a is equals to 0. We have already know that a is equals to 0, so substitute a is equals to 0, b sin ka. So b sin ka is equals to 0, but we cannot substitute b is equals to 0, because if b is equals to 0 then equation 4 becomes 0, which is not possible, and that is the reason we will not substitute b is equals to 0, but we will equate sin ka is equals to 0. So if you write sin ka is equals to 0, we can write it as k is equals to n pi, because 0 we can write it as sin of n pi is equals to 0. So in that way we can write k is equals to n pi, or k is equals to n pi divided by a. Now we have got the value of A and we have got the value of K. So substituting the value of A and K is equals to n pi divided by A in equation 4. We will be getting psi is equals to B sine n pi divided by A into X. So we have got the value of psi is equals to B sine n pi divided by A into X. This is the wave function. Now in this wave function still the value of B is unknown. The value of B is unknown. So to find out the value of B, we will go for the normalization process. So by applying normalized wave condition for one dimensional case. So normalization condition means it is integrating. So we are going to integrate from 0 to A modulus of psi square dx is equals to 1. So psi is nothing but B sine n pi x divided by A wave function. So we are integrating it in between the limits of 0 to A. So it will become B square into sine square this theta is equals to 1. Since we know that sine square theta is equals to 1 by 2 1 minus cos of 2 theta, we will replace this sine square by cos of this whole term. But we know that cos of integration cos of 2n pi x divided by A into dx is equals to 0, and that is the reason this whole term is going to be 0 and we will be left with only b square divided by 2 integration from 0 to A dx is equals to 1, or b square divided by 2 x limit from 0 to A is equals to 1, or b square A divided by 2 which is equals to 1, or b square is equals to 2 divided by A, or b is equals to root of 2 divided by A. So substituting this b value in the wave function equation, we are going to get psi is equals to root of 2 divided by A sine of n pi divided by A into x. This is the wave function equation where n can take all possible integral values. Now we will go for the energy eigenvalues. So this above equation represents eigenfunctions of the particle inside potential well. For each eigenfunction, we associate an eigenvalue, that is allowed energy associated with that particle. So from equation 3, we have k square is equals to 8 pi square m divided by square into E. And we also know that k is equals to n pi divided by A. So substituting this k value in this equation and writing the value in terms of E. E is equals to n square h square divided by 8ma square, where n is the quantum number, En is the eigenvalues, and if you substitute n is equals to 1, in this equation if we substitute n is equals to 1, we will have E1 is equals to h square divided by 8ma square, and this E1 is called as a 0 point energy or ground state energy. So thank you dear students.